Alright, this is going to be another Codeforces editorial for contest 1512, round 713. So this one is pretty old. I think it's from early 2021. So once again, I'm going to gloss over the problem statements for the most part, as well as assume that anyone who is watching this has read the problem statements. I think my solutions are intuitive and easy to follow, even though they might not be 100% optimized, so keep that in mind when looking at my code or reading this document of notes. So the first problem, SPY detected, there's many ways to solve this problem. I've chosen to do it in a way that uses O of one space. So the first number we read in, we take that as num1 in increments count, and the last, this is the last index we've seen it at. So obviously in this case that would be 1. So you want to maintain these two variables for both of the numbers that we are going to see in the array. So whenever we eventually see a number that's not num1, we set num2 to that number, increment its count, and then the last time we see it is whatever index we're on right now. So we loop over the array, maintaining these variables, and when we get to the end, one of them will have a frequency of 1, since it's a SPY. And if it does, then the last time we saw it is also the only time that we saw it, which is its location. So if that turned out to be num1, number we saw at the beginning, we output the first index. Otherwise, it was the other number, num2, so the last time we saw it was the last 2, since we've been maintaining this by rewriting it every time we saw it. So this is the location of num2 if it's a SPY, so we just output, whichever one. So I like this solution because it's O1 space. We're just maintaining these few variables. We're not storing the array, but it's also it's still O(n) times, since we need to look at all the numbers to find where the SPY is. So no escaping that. All right, on to the next one. Get the problem list here. So almost rectangle. For a human on paper, this problem would be very easy, but of course I'll go over the strategy of how we can implement that in a computer. So if 2 points are on the same row, so let's say we have this, then we can just add our 2 points on the same column, so one on this column and one on this column. So we could just do like this. For simplicity, if the top row is open, I'll always put it there. But if we had an example like this, the top row is the row that the 2 given points are occupying, I can just do this. Same goes for columns. So if this was our example here, 2 given points on the same column, they're on the leftmost column, so I can't use the leftmost column. I just do this. Go to the second column. So here, top row is occupied, I went to the second row. If the top row is not occupied, or left column, I mean, is not occupied, then I just use the left column. Then there's the situation where they're diagonal. So we have something like this. They're on different rows and different columns, diagonal from each other. So we'll call this R1C1, R2C2. So we need to find locations to put 2 points, RC3C3, R4C4. So here, R3 needs to take one of the rows and one of the columns, so R1C2 or R2C1. So I will do R1C2 here. And then R4 needs to take the opposite, so R2C1. And that's how we get here. R2C1. So it's on the same row as R2, same column as R1. So this is R4, this is 0.4. This is 0.3. And this is on the same row as 0.1, same column as 0.2. So there's our rectangle. Onto the code. We look for the two given points, store their coordinates. If they're on the same row, if we can use the top row, we do it. If not, we use the second row. Same with columns. If we can use the left column, we do it. If not, use the second column from the left. If they're diagonal, then take one of the points. Take one of our added points should have the row of the first given point and the column of the other one. The other added point should have the row of the second one and the column of the first one. Then we simply output our board. If we're on any of our 4 points, then we output an asterisk. Otherwise, the cell is empty, so we do a period. Pretty basic there. So this takes n squared time, since we need to look at the entire original board to see where our given points are. And it is O of n space, since we read in one row at a time. So we read in this row, then this row, then this row, then this row. So each row is O(n), so it takes O(n) space. There's probably a way to read in one character at a time to get down to O(1) space, but the rows don't have white space, so you would need some special steps for that. So I just read in one row at a time. It's more convenient. Third problem, AB palindrome. So I'm going to refer to n as the length of the string a plus b, and indices I and n minus I minus 1 are considered a pair. So what I mean by pair is they're like mirror counterparts. So if I have some string like this is the middle point. This index and this index are partners in a pair. Same with these two. Same with these two. Because in a palindrome, this has to be the same as this. This has to be the same as this. This has to be the same as this. So obviously this is not a palindrome. This goes the same as if we have a odd length string, like this. So this is obviously not a palindrome since this is the middle. So this index is paired with itself. So this can be anything in a palindrome if the length is odd. These are not the same, so it's not a palindrome. But these are a pair, these are a pair, these are a pair. Okay. So we have a two-step strategy to solve this problem. So the first step is balance S first, turning question marks into zeros or ones. So what I mean by that is if I have a initial string, let's say it's like this. So this is the middle dividing point. This is a pair and this is a pair. So if we are going to succeed in turning this into a palindrome, this has to turn into a 0 because we can't change this index. Likewise, this has to change. This has to change into a 1. So our first step is to balance the question marks. In some strings, there will be a pair of question marks. So, so 1, 2, 3. So this is the middle point. So here we have a pair of question marks. So there's a pair with both question marks. We're just going to ignore that for now. We'll worry about that in the second step. We just want to balance pairs where they have one question mark and one number. So this one would have to be 1. This one would have to be 0. So we read in our string, and I'm going to make it a vector of characters in order to more easily work with it. So 0 is represented as 0, 1 represented as 1, and question marks are represented as 2. So we're also going to maintain a count of how many zeros and how many ones we've used so far, because we need to compare that to our quotas at the end. So if we see 0 increment, 1 increment. So if by the time we read the original string and before we've done anything, if our counts are already beyond what they should be, we can't do anything to change that, since we can't decrease the counts. So we just fail immediately here without doing anything if that's the case. Otherwise, we go to our first step, which is balance, which, like I said, a pair with one question mark and one number. So if left is a question mark, represented by 2, and right is a number, make the question mark on the left equal whatever number was on the right, update our counts. Same if the question mark is on the right and the number is actually on the left, assign the right index to the left and update our counts. Otherwise, so this case is if we have a 0 and a 1. So neither of them are question marks, but one of them is 0 and a 1. Since we can't change numbers that are already set, there's no way to balance this, so we just fail. There's no way to make it a palindrome. So that's like in this example here. We didn't write these. These weren't question marks. They were set numbers, but since they're a pair and they're different, we can't balance it. So we just return -1. I forgot to go over this loop goes up to n over 2, since we only go to the middle point. We go here, because when we're here, we also check this one. We check its partner. Here we check its partner, here we check its partner, and the middle one, we worry about this at the end. So by iterating to the middle point and checking its partner, we check every index, except the middle, like I said, which we'll worry about later. So now we only have pairs of question marks left. So in this example here, we balanced these pairs. So now there's still this pair left with question marks. The only question marks that exist now should be in pairs of question marks. So if, since we've modified some of the question marks into numbers in the balance step, we check again to make sure that our counts are valid. If not, fail. Since when we balanced, we didn't have an option on how to balance. If there was a 0 and a question mark, the question mark had to become a 0. There's a question mark and a 1, question mark has to become a 1. Another check we have to do is if our counts are odd. So if our counts are odd, then it is not possible for us to proceed, since it means that if our counts are both odd, one of them has there's going to be some pair somewhere that is a pair of a 0 and a 1. So that violates the palindrome characteristic. So now we fill any pair of question marks. So again, we iterate up to the middle point, checking the index in the left half and its corresponding partner in the right half. If v left is a question mark and we have at least 2 zeros left, we can make them both zeros. If we don't have 2 zeros left, then we turn them into 1s. So the last check, if our string is odd, there's that one character in the middle that we haven't examined at all. So it might be a question mark. If it is, and we have a 0 left, turn it into a 0. If we don't have any zeros left, then turn it into a 1. Final check, make sure our counts of zeros and ones are what they should be. Make sure we have no question marks left. There shouldn't be any. And then we simply display our answer. So that takes O of n time. Remember, n is a plus b, so we need to look over the entire string. We visit it a few times when we read it in, when we balance it, when we fill it, when we check it. So our steps, we visit each index once for every step. And there's also O of n space, since we store the string or vector of characters in this case while we work on it. So yeah. Problem D, this one's interesting math problem. So the strategy of the problem is as follows. The sum of elements in B is the sum of the elements in A, since we have all the elements in A, B sub n plus 1, here B sub n plus 2. B sub n plus 1 is the sum of the numbers in the array A. So it can be rewritten like this. So b of n plus 2 is x, we'll call that x. First we read in b and keep account of each value of values we see in b. So if we read this in, we would have 2 2s, 1 3, 1 7, 1 12. There are a few conditions we need to we iterate over all of the values in our map. So we would check 2, check 3, check 7, check 12, we already checked 2. And we need to find x. If we find a valid value for x, we're done. That's our solution if we can find a valid x. So we're going to iterate over the values, like I said, 2, 3, 7, 12, and a number can be a valid x if the following conditions hold. Sum of b minus x should be even, since sum of b minus x is 2 times the sum of a, and obviously this number should be even. Sum of b minus x divided by 2 equals sum a, so just divide by 2, we get sum of a. This should be a value that we saw. This number should appear in b, since the sum of a is b of n plus 1. So we should see this number. We should see sum of a at some point. Well, this number, I guess. That's the second condition. Third condition is if the number we're testing to see if it can be a valid x should not equal this number, sum of a, unless we saw this number more than once. So we'll get to why that's the case in a second, because it might not be that obvious. Obviously, if we go through the whole map and don't find any valid x, we output -1 because there's no solution. So why is this condition so? This is because sum of b minus x divided by 2, so this number, is this number. Okay? And also, x is this number. So if x is equivalent to this number and equivalent to this number, we had to have 2 copies of it. Otherwise, if we only had 1 copy of it, then both these numbers can't be the same. And if our equations turn out that way, that x equals sum of b minus x divided by 2, that means both of these numbers need to be x. But if we only had 1 copy, that's not possible. So it's not a valid x. It's a contradiction. So here's an example from one of the later tests. We have 4 1s and 1 2. The sum is 6. We check our first condition. It's even. 6 minus 2 is even. This is when we're checking if 2 can be a valid x, by the way. 1 does not work. You can try that for yourself if you want. But let's test 2 as our x. So we see that sum of b minus x is even. 4 passes. 4 over 2 is 2, and we had a 2, passes. However, x equals 2. 2 equals 2. But we only saw 2 once. So b of n plus 1 and b of n plus 2 cannot both be 2. But if b of n plus 2 was 2, then b of n plus 1 also had to be 2. So b of n plus 2 cannot be 2. Once we find a valid x, we can decrement its count in our map by 1. So in this example here, 2 is a valid x. So we had 2 2s, we decrement 1 because there's only 1 in the original a. And we decrement sum of a, aka b of n plus 1. So in this case, b of n plus 1 is 12. So we remove the 12, and this is our original array A. So we go through our map at that point and iterate over the keys and their frequencies, whatever their frequency is, we output the key that many times. So count the frequencies for B, get the sum, check our first condition is 2, so this is 2 times the sum of A. Is 2 times the sum of A even? Yes. Is, did we see A sum? So A sum, 2 times A sum divided by 2 is A sum. Did we see that? Is this frequency at least 1? Yes. Okay, then a sum cannot equal x unless we saw this number twice. That way there's a copy for a sum and a copy for x. If all these conditions are true, we found an answer. Decrement x, decrement a sum, since those elements are only in B and not A. And then simply iterate over the map for every value, whatever its frequency was, we output that value that many times. Simple enough. And log n, we use a map. Insertion into a map is log n. We do it n times, so n log n. Space, the map can have n entries, so it takes n space. Okay, next problem. Permutation by sum. So the strategy for this problem is to fill in L and R, LR first, that segment, because once we have that done, we can just use all our unused numbers into the rest of the array with no care about what order they're in. So if we have say this is L, this is R. Once we get our numbers for this, so let's say 1, 5, 6, so there's 7 spots here. Then we didn't use 2, 3, 4, 7. We can write 2, 3, 4, 7 into these 4 indices, and it doesn't matter what order we put them in. So we could do 4, 3, 2, 7, 7, 3, 2, 4. It doesn't matter. As long as we use our unused ones in all the indices outside of this segment, it doesn't matter. So a consequence of this is we are free to choose any numbers to satisfy the sum within this interval. Any numbers we need to make this possible, as long as they're between 1 and n, and no duplicates. So the first observation is we can choose we can get the sum s. There is a solution as long as s falls into the following range. So as long as s is in the following range, k largest numbers, sum of large k numbers, k largest, and sum of k smallest. By the way, k is the size of the interval of the segment. So k equals r minus l plus 1. So this is obviously 1, 2, 3, 4 up until k. This is n minus 1, n minus 2, down to n minus k plus 1. So as long as s is within this range, we can there is a solution, basically. If s is outside this range, we just return -1. So let me pull up my code to illustrate this. So if so yeah, I used Gaussian sum here. So Gaussian sum is just 1 plus 2 plus 3 all the way up to n equals n plus, or n times rather, n plus 1 over 2. This is a basic math formula that we can use to our advantage in this problem. Can I select? There we go. So we have Gauss k, since we're summing up from 1 to k, and this is Gauss n minus Gauss n minus k. So the reason for that is Gauss n is this, Gauss n minus k is this. actually, for clarity, I can do it like this. So this is Gauss n, this is Gauss n, this is Gauss n minus k. So if we just chop off the first, if we just subtract all these terms, we chop off this, then we're left with n minus k plus 1, n minus k plus 2, all the way up to n. So that's what we want, the k-largest numbers. So again, if s falls into this range, we're good to find a solution. Otherwise, there's no solution that's possible, so we just terminate. Because we can't get a smaller quantity than this, we can't get a larger quantity than this. So otherwise there's some solution. We can construct the interval LR this way. So we will begin by, let's just say, I'll draw this again. Let's say our interval is 3, 4, 5, 6, 7. Let's say our interval is this. So it's 3, it's size 3. So we'll start with 1, 2, 3 always. And we'll increment. So let's say S is 10. So the maximum, or actually, let's do 12. So the maximum value we have available is 7. So we say, okay, if I turn this value into 7, is it enough? So I'll always start with R. That's the starting point for our strategy. I'll say, if I turn this into 7, is it enough? So our current sum is 6. If I turn this into 7, our sum will be 10. So I say, okay, that's not enough. So I turn it into 7 anyway, and then I move to this index now. So what is our sum is 10. What's the maximum value we have now? The maximum value is 6, because 7's already used here. I say, is 6 enough? If, or rather, a better way to look at it is, our sum is 10 right now, and we need to get to 12. So we need to increase this number by 2. Is the number 4 available? Yes, number 4 is available. So we do this. Then we're done. So the strategy is start with the rightmost index in this segment, increment it as far as we can, or however much we need until it's done. So if we started with 1, 2, 3, and S was 8, we only need to increment this to 5, and then we're done. But in this case, increment it to its maximum value 7 is not enough. So we increment this maximum value and then take one step left, and then repeat the process here until our sum matches 12. So once we replace this with 4, our sum is 12. Done. So repeat this process until we reach sum n. When we go from here, we don't actually check 3, 4, 5, 6, 7. We just say 7 is the maximum value. Check if that's enough. So it can be done in constant time for each index. Also, we won't have any duplicates since once 7 is used here, the maximum value for this index becomes 6. So if we're incrementing this index, we can never pass the value of any index to the right within the segment. Once we have our interval, so our unused numbers were 2, 3, 5, 6. We just fill in 2, 3, 5, 6 here. So you can have a vector of booleans. So originally we were using these numbers, but then we changed 3 to 7, we changed 2 to 4. So then 1, 4, and 7 were used, and these numbers were not used. So these numbers get put into here, the indices outside of our segment. So that takes O of n. So we we iterate from right to left in our segment if we can reach the sum in this index. If we can reach the sum by incrementing this index to some value, we do it. Otherwise, we just increase it to the maximum and then jump one spot left to continue the process. Then at the end, we have this used vector where we keep track of the entire time. We keep track of what elements have been used and which ones have not, and then we fill in the rest of the permutation with the unused elements. So you can have a look at this code, examine it more to see exactly how that works, but it's pretty straightforward. So it's O of n time, since we spend constant time on each of these indices and a constant time on each of these indices. So O of n time. It's also O of n space, since we are storing this permutation the entire time that we're working on it, and we have this used vector, which is size O of n as well. So O of n space. Okay. Next problem, education. This is a interesting problem in my opinion. Dynamic programming. So I want to start off with two key observations that are necessary to solve this problem. The first is we can see that there's potentially levels within the company that are not worth climbing to. So let's say we're at some position that gives us 10 tugrix per day. The next position pays us 11, so an increased salary if we get promoted. But the course to get to the next position costs 50 tugrix, and we need 95 tugrix to buy the computer. So if we just stay at our current position we're at, collect our 10 tugrix per day, we will reach our goal in 10 days. On the 9th day we'll have 90, on the 10th day we'll have 100. So we can buy on the 10th day. However, if we try to get to our new position, we'll spend 5 days saving up for the course, since we need 50 tugrix. We need to spend 1 day taking the course, and then we need to spend 9 days saving up. So by the time we get to our position, 6 days will have passed, we'll have nothing saved up, and then it'll take us 9 days on this salary to save up. So on the 8th day we'll have 88, and on the 9th day we'll have 99. So that's 9 days saving up, plus the 6 days we spent saving for the course and taking it. So that's 15 days total, which is clearly slower than if we just stayed at our original position. So now we can see that potentially there are positions in the company that are not worth climbing to. That is a potential situation. Second, let's assume that there's a position in the company that is worth climbing to. And don't worry about the worth climbing to part, we'll take care of that later. But let's assume there's a position in the company that is worth climbing to. We should get there as soon as possible. And I'll demonstrate this with another example here. Our current position has salary X, the next position has salary Y. And let's assume that the position with salary Y is worthwhile to get to. Let's say it takes 5 days to save up for the course. If we save up for it and then take it immediately, 6 days after we take it, we have 6Y saved up. This is the increased salary. If we delay it by a day, we get X extra money, since we stay on our original salary. But 6 days after we had enough money to take the course, we only have 5Y plus X saved up, since we spent an extra day here delaying our promotion. Same goes for if we delayed it by 2 days. We get 2x money, since we spent 2 extra days at our original position, but we missed out on 2 days of increased salary at position Y. So Y is greater than X, so we missed out on Y minus X tugrix every day that we delayed our promotion. So on this day, we could have been earning Y, but we were only earning X. So our strategy boils down to the following. There is some optimal position in the company that we should get to as soon as possible, and then we just stay there saving up money with that salary until we have enough to buy the computer. So for each position in the company, let's calculate how long it takes if we speed run our way there, how long it takes for us to save up for the computer once we're there, because that's the total amount of time, and that's what we care about. So And then if we can do that for every position, we can just go through all the positions and pick which has the shortest total time. So um, let's first compute how long it takes to reach the position. So in our code here, how long does it take to reach position I? So obviously to reach position I, we had to reach position I minus 1. So our time it takes to reach position I is the time it takes to reach position I minus 1 plus the number of days it takes for us to save up enough money for the course to get us to position I. So the course cost is B I minus 1, since course I minus 1 gets you from position I minus 1 to position I. So the cost of the course, any remaining tugricks we have after reaching I minus 1 from position I minus 2. So if our course costs 20 tugricks, let's just say we had 18 saved up, and our salary is 3 per day. On the seventh day, we'll reach 21 tugricks, take the course, and then when we reach our new position, we'll have 1 tugrick saved. So we'll also keep track of how many tugricks we have after each promotion, since that can contribute towards the next course that we take. So course minus whatever savings we have left over divided by our salary, and we round up. So this is a trick to round up with integer division. I won't explain that since I think I've done it a few times on this channel, but you can work out the math for yourself. So course cost minus savings divided by our salary, rounded up, and we need to update our savings after we take this course. That way we can do the same calculation for future promotions. And we also need 1 day to actually take the course. So this is the total amount of days it takes to get to position I. Now we need to calculate, once we reach position I, if we were to never attempt to get promoted again and just sit here on this salary, how long would it take us to get our computer? So cost of the computer minus our saved tugricks upon reaching this position divided by our salary, rounded up. This gets added on to the count of how many days it takes us to get here, since the total amount of time we care about is how long it took for us to get here plus how long it takes to save up if we stay at this position. Then we simply keep track of the best position in the company, the one that gave us the shortest total time to get there and save up once we got there. Then we simply output whatever shortest time there was. So cool dynamic programming problem there. O of n time, since we need to do these couple calculations for each position in the company. Also O of n space, since we're keeping track of this total time as well as how many tugricks we have left over following each promotion. Alright, last problem, short task. So this is going to be our strategy. Our strategy is going to be, we compute t of I for all I up to 10 to the 7, which is the upper limit on C. We can do this using the sieve of Eratosthenes. So normally with the sieve of Eratosthenes, you iterate over every prime, and every multiple of that prime is marked as a composite number. But instead of just marking numbers as composite, we are going to add whatever number that we're iterating over multiples of, we add that number to a running count of each number that it would have marked. So if I do an example, let's say I'll go up to 10. We start with 1, and we add 1 to every multiple of 1. So every number is a multiple of 1. So we do this. Then we go to 2. Add 2 to every multiple of 2. Go to 3, add 3 to every multiple of 3. 4, add 4 to every multiple of 4, and so on. So then if we were to sum all of this, this up a little bit so I have room to write the sums. This would be 1, this would be 3, 4, 7, 6, 12, 8, 15, 13, 18. So once we have this, so this goes all the way up until 10 to the 7th, we have another array in which the indices are these values. So what do I mean by that? I need to widen this. So I have another array. So this is our actual answer array. So say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, so on and so forth. Again, up until 10 to the 7th. So this is C, basically. These indices are C. So I say, okay, I'll iterate over this array and say, okay, what is D of 1? D of 1 is 1. So I go to 1 here and do this. Then I go, okay, 3. What's D of 3? D of 3 is 2, since 2 is the index that had this. Or D of 3 is 2. And all of these, so 2 is empty. There's no number where there's no number I that D of I equals 2. So I go, okay. Next one, 4. D of 4 is 3. D of 7 is 4. D of 6 is 5. D of 12 is 6. 8, 7, 15 is, so, well, I'm not gonna, here, 13, 14, 15 is 8, 9, and then 10 is further left. But I would have to come up with a specific example, but it's possible that there's a repeat. So let's say 10 is 18. It's possible there's some other number that's more than 10 that's also 18. So when I get to that number, I'll say, okay, D of whatever this number, I'll call it K. D of K is 18. So 16, 17, 18. So I wrote 10 in here, right? D of 18 is 10. If I get to this number, I say, oh, D of 18 is K. So I go to index 18 in our answer array, but I see, oh, there's already a number written here, 10. Because 10, I would encounter 10 before K, since K is greater than 10. I don't update this index with K, because we want the minimum number. So once a index has been initialized, it never will get updated by a later number. And then if so then if the test case asks me, okay, C equals 12, I just go to 12, check what number is there, 6. 6 is the minimum number where the sum of its divisors are 12. C asks me for 14, I go to 14. There's no number there, return -1. And we're going to pre-compute this in main, since this sieve is the same always. It doesn't, like, C is just a query. That doesn't affect our data structure, so we just pre-compute this one time at the beginning, and then the queries can run in constant time. So for each number, add it to the running sum for each of its multiples, then fill in our answer. So if our answer at this index has not been initialized, then whatever the value in the sieve was, put the index that had that sum in there. And if it's over 10 to the 7, then we don't need to worry about it, since C is 10 to the 7. So if there is a number that has a sum of divisors greater than 10 to the 7, that will never be an answer for any test case, since C can only be 10 to the 7. So the runtime of this is n log n, and the reason why is because when I is 1, this will run n times. When I is 2, this will run n over 2 times. When I is 3, n over 3. So we get this equation. This is the harmonic series, and it converges to this, so you can look up that if you're curious why that's the case, but it takes O n log n time to run this loop and initialize our sieve. Then it takes O(n) time for us to fill in this our answer vector, and then we can deliver every query in O of 1 after that. So n log n time, where n is technically 10 to the 7th, but since that's the upper bound on n, or c, I've chosen to do n log n. Space, again, this should probably be O of n since that's the upper bound, but it's technically a constant space since the problem constraints are bounded to 10 to 7. So I guess I should do this. So I'll update my document with that change, but yeah, so these are the bounds of n log n, and then O(n) space since we have these two arrays. So yeah, I hope these solutions and explanations were helpful. If you have a question, feel free to leave a comment or message me directly on Codeforces. I think my profile is listed in my channel description, so check that out if you need to send me a message directly. Hopefully these were helpful, and I'll see you in the next video.